We're deeply touched and honored to receive this award. It made a huge difference to our lives. Let me go on to the next slide. Here's Luca. We're really sad not to be in Luxembourg today because of prior engagements. But we got together on our mobile Ambients, I think probably 2 laptops, over Teams a few weeks ago, and had a bit of a discussion about what to say. And the organizers asked for a reprise of the talk from FoSSaCS 98. And Luca did it the first time, so we decided it was my turn after all these years. And I'll just say, just on a personal note, I'm just hearing your voice. Is there a problem?
It's all good. We hear you well.
Fantastic, thank you. Yeah, on a personal note, it really changed our lives because we were, going back to the, hang on, let me bring a pointer. Luca was doing the work when he was at this amazing corporate research lab called DEC-CIRC that was in Palo Alto, California, and I was at the University of Cambridge as a Royal Society University Research Fellow. And we started working on this in September 96, and in middle of 97, Luca came to visit me in Cambridge, and that was the time that Roger Needham was setting up what would become Microsoft Research Cambridge, and he was looking to hire people. And in the tea room, Luca came in, and a veteran of a corporate research lab and a stellar programming language researcher, and so he ended up hiring Luca, and then I sort of joined shortly, or I applied and joined shortly afterwards. So doing the ambient calculus meant that we both ended up joining Microsoft, which was a huge deal for both our lives. We both now left. I left about 6 months ago, and I now work in London for a software synthesis company called Cogna, and we're using natural language as a programming language, which I'm very excited about. But let me just refresh your memory about mobile ambience. What was mobile computing like in 1997? Mobile computing was things like laptops or PDAs, like the Palm Pilot, or you have feature phones. Just to put it in context, it was 10 years after that Apple came out with the iPhone. So we didn't have smartphones in 97. And mobile computation, people in programming languages had got very excited about Java and mobile applets where the code would move. And we started to think about whole computations moving around. So 2 things were happening. There was mobile computing, mobile hardware, in other words, and mobile computation, mobile software. And we wondered about how to think about these different kinds of computing. And also, there was a security aspect to it, that you needed to have some kind of borders. So, software agents might move around across the network or be carried in a laptop. Computers themselves, like laptop computers, would move around physically, and there would be things like boundaries of physical buildings or virtual firewalls. And we just wondered about having some sort of formalism or some sort of understanding of these kinds of mobility. So this slide describes the philosophy of ambience, kind of postulates for mobility, that there are distinct locations, that if locations have different properties, then people and programs will want to move between them, that we might need to set up some barriers to mobility, some gatekeeping to preserve properties of locations. And even so, people and programs will need to cross these barriers. So that was like the philosophy. And then we formalized it in a calculus called the ambient calculus. And it started formally from the pi calculus of Milner, Paro, and Walker. And I mean, it's a theory of processes, and the interaction is via shared names. And it was always described as a process calculus of mobility, but the mobility was really that you could send channels around. There wasn't really a sense of a location or a container. And things like failures had been studied, but there was not really a direct account of access control. In the ambient calculus, we had the notion of multiple disjoint locations, and interaction was by being in the same place. So communication was within an ambient, and mobility was about crossing over barriers, and and locality was really about a sort of topology that was encoded within the processes, and failure amounted to unreachability. And then an important idea was capabilities, that you could use names to regulate access to these different containers, as we'll see in some examples. So then, what is an ambient? An ambient is a place delimited by a boundary where computation happens. And ambients have names, and within them they have a collection of local processes and possibly a collection of subambients. And ambients can move in and out of other ambients, and they do that by using capabilities that are built from ambient names. And just as in the pi calculus and the SPI calculus, which is a theory of cryptography and cryptographic protocols that I'd worked on previously, ambient names are unforgeable. So it's a particular sort of abstraction of reality. Here is the formal grammar of the ambient calculus, and what I'll do is talk through it in parts. And quite a bit of it is standard from previous process calculi. So the P stands for processes, and M stands for values or capabilities. And these constructs here are the same as in the pi calculus. And these constructs here, like ambient construction, exercise of capability, and a local input-output, those are specific to the ambient calculus. And then this syntax here was also specific to the ambient calculus. We used a style of semantics based on Berry and Budol's chemical abstract machine, which came out in the, I think about 91. And Robin Milner there already had been a formulation of the pi calculus using label transition systems, but in a sabbatical in France, Robin Milner had worked, I guess, discussed with Berry and Budol, and had come up with a reformulation of the pi calculus in the style of the chemical abstract machine. And he described the, so let's see, a process represents the state of a computation, and the semantics is based on a reduction relation, meaning that one process can evolve into another. But also another relation that was very important was process equivalence, written like this, or structural equivalence with a congruence with these three bars. And so arrow is real computation, while structural congruence is rearrangement. And that is something we took directly from Milner's work. And then in terms of semantic equivalence, we used a notion of observational equivalence I'll get to later on. So straight from the pi, so let me go through the constructs one at a time. So we have parallel execution, and these rules are just the same as in the pi calculus, that if you have the parallel composition is a congruence operator. So if you have an evolution of a process in a larger construct P par R, then that larger construct can evolve to Q par R. And replication is like an infinite array of copies of P. And so it can be rearranged. You can always peel off as many copies of P as you like. And then restriction is this cool algebraic formulation of fresh name creation that came from the pi calculus, and it exploits the scoping rules taken from the lambda calculus. But a key idea is that if you have a fresh name outside a composition, and the name is known within Q but not within P, then we can sort of move the fresh restriction operator within the composition. And like parallel composition, it's a congruence. And then we also have an inaction operator 0 that has some standard rules. Let me get to ambience. So this is the syntax for ambience. N is the name of the ambient, and P is the process running inside it, and it's a congruence rule. So P is actively running inside an ambient. And then we have capabilities that are written like this. So M.P is a process that is going to perform an action by executing this this capability M. And let me go through, there's three base capabilities for entry and exit from an ambient and for opening an ambient. So I'll go through each of those rules in turn. So here's the syntax for an entry capability, and this is an action that is going to move an ambient inside another one named M. And maybe it's easiest to see this rule in terms of a picture. That you've got an ambient named N, and you've got a process, one of its top level processes is sort of in charge of the ambient, executes this capability, and it has the effect of moving the whole enclosing ambient together with any other processes within Q, which could be other subambients, or it could be running other active processes, moves that whole thing within M. So you get this rearrangement where the N ambient is now nested within M. So that's entry. And then exit is the other way around. Again, let's look at the picture. We've got an ambient named N that's nested within another one. And there is some other sibling processes, like again, it could be sort of active threads or ambients that are running alongside N, but running the capability out M within that moves the whole ambient N, including anything else, to be outside its previous container M, and so it's now at the top level. So those two rules are the core aspects of mobility in the ambient calculus. And then there's an operator called open that is like the opposite of ambient creation. It kind of tears down an ambient. So its rewrite rule looks like this. And again, thinking about it pictorially, you've got an exercise of a capability here, open N outside an ambient named N, and this has the effect of ripping down the barrier, and anything inside the ambient named N now spills out and now is at the same level as P, and then they can press on. And then finally we have input-output operations. And in the Pi calculus, input and output actions take place over channels, and in the ambient calculus, they're really like local anonymous communication, like not on a name, within an ambient. And so the reduction rule looks like this. If you've got an output of a term alongside someone who wants to receive it, then they can interact and the message will flow into the continuation of the input action. And so this is like local communication. And we do not allow, as a primitive anyway, long-range communication. That needs to be encoded as, say, ambients that migrate around. Okay. So we have some, I've mentioned a whole bunch of equivalences, but there's some interesting inequivalences. So replication creates new names. So this is exactly as in the Pi calculus. A replication of restriction makes unboundedly many names. So it's not the same as pulling the restriction outside the bang. The guy on the right only has one copy of N. The guy on the left has got many copies of N. So these aren't equivalent. And then also multiple ambients named N have a separate identity. So you can't just conflate two ambients named N. It's useful for redundancy to have multiple ambients with the same name. And also, frankly, it's hard to rule this out. So we didn't attempt to do that. Expressiveness, as Peter said in in his lovely words at the start of this talk, the ambient calculus is highly expressive. So here's a list of like existing concepts that could be represented, like synchronization and communication. I'll sketch later how Turing machines can be represented. And I had to remember how I had to think again about how to represent arithmetic. You basically can represent a number as a sort of tower of ambience of height n. And data structures, a thing we discovered as the years unfolded as we were studying ambience is that the ambient calculus could really represent really rich data structures. So we understood early that it could represent XML or things like heaps, but also like today's JSON. All of these constructs could easily be represented as processes in the ambient calculus, but intermingled with active threads. And then we could represent formal calculi of like the ones I mentioned here. And then the original motivation, of course, was to represent lots of net-centric concepts like these mobile PDAs and mobile code and mobile agents and so forth. So a whole lot of these kind of concepts can be represented. And when I was working with Luca on this, we had such a lot of fun coming up with a bunch of examples of these sorts and encoding them. And the long version of the Ambients paper that was in Theoretical Computer Science, I think in 2000, has a great many examples of this sort. And I don't have time to go through them all. I wanted to put this one in because it was kind of like a lot of fun when we realized that you could have a really natural encoding of Turing machines in the ambient calculus. I'm not going to give you all the details, but hopefully you can get the idea here that a Turing machine can be represented as a sort of tower of ambience, where the top of it is an ambient named end, and then and it's like the first square, if you like, and it has a sort of state S, a symbol S0. And then the next square is, or symbol S1 is nested within an ambient that's named square. And then we have another ambient named square to hold S2 and so forth all the way down. And then you have a process, an active process called extend right at the bottom that is going to basically just keep going because we have to represent an infinite tape in the to represent the Turing machine. And so what this process can do, and this takes a few lines in the calculus, is that it can basically just keep going and make a deeper and deeper tower of ambience of squares containing fresh symbols. And similarly, we can also extend left, so we can do some fancy footwork and take this whole tower and sort of move it into, or add a new square that contains this tower and then put that within another top level ambient named end. So the details are kind of tricky to write down, but they all work. And then you have a head here that's an ambient that moves up and down this tower representing the Turing tape. Let me give you another example that illustrates all the constructs before I end this part of the talk. This is one of, I think this is Luca's journey to Europe from the US, from San Francisco Airport to Charles de Gaulle Airport via this the AF-81, I guess Air France aircraft. And he wondered about how to model his journey using mobile ambience. And this is the gist of it, where we're using ambience like this ambient here to model the airport, SFO, and also eventually CGG. And then the ambient Joe is like Luca. It's the tourist who is going to make their way in the aircraft. Here's the aircraft here that initially is at SFO. And the ticket desk is just giving out tickets to get into the plane. And the ticket is a capability that can be communicated that knows the name of the ambient at the source. And also it's going to rename itself when it ends. And then at that point, the tourist will get out. So what the code here is showing is that you've got the ticket desk in parallel with the tourist, and then they communicate. And so you end up in this situation where Joe has got this capability and is sitting alongside this ambient. And so the capability, the first part of it fires, and Joe moves within the aircraft ambient. And then this route here is going to cause it to move. And this is where we're pressing the details, but cause it to move to the airport, and then eventually Joe will step out. So that wee example, and the full details are in the paper, show all the constructs of the ambience in one go. And here is the long example of firewalls. I'm not going to go through it. Some examples in the ambient calculus can get quite complicated. I promised I would say a bit about contextual equivalence. We define it in a standard way without mentioning any construct. Well, we do. The exhibition of a name is that you have a top-level ambient named N that is not restricted, so N is not in this restriction. And you can define contextual equivalence in the standard way. When we submit it to FoSSaCS, we kind of joked, we'll absolutely have to have a theorem, because so far all we have is reduction rules and lots of examples. And we figured out a rather nice equation that if you have an ambient named N, and its name is secret so that nobody outside it can interact with it, then it's basically equivalent to the inactive process. And this is pretty intense, because this ambient isn't necessarily inactive, because P may know the names of other ambients, and so it can be active on its own, and it can also move around sort of silently. But because nobody knows the name of this ambient, it sort of perfectly acts as a firewall, and it prevents any interaction between P and the outside, and so it's basically the same as zero. Okay, that was the end of the talk from FoSSaCS. I just want to say a little bit before I finish about the influence. We banged a drum and wrote several papers about ambience following FoSSaCS. We did a paper about types, mobility types, equational properties, and logics. And I learned a ton about substructural logics and types and equivalents working on this. We were fortunate to have colleagues who challenged some of the ambient calculus assumptions and investigated variations. There was a ton of good energy. So there's some papers here from about secure, safe ambience, about boxed ambience, and so forth. It was great to be in a dialogue with Robin Milner. I've explained that we built on his work very much, but we were really happy that he built on our work as well. And he developed his theory of bigraphs, and one of the motivations of his theory of bigraphs actually was to be able to represent in a sort of larger framework both ambience and the pi calculus. Biology, a very influential paper about building on ambience was by bioambience, and it was so Ehud Shapiro was got to know Luca and wondered about how to model biology and cell biology in particular using process calculi, and together, especially with their Shapiro's student Aviv Regev, came up with a formalism called bioambience that showed how the how to represent biology, and she's now a very distinguished professor at Genentech. Origins, very rapidly, we first invented the ambience at a functional programming conference in September '96. The two of us met up and had the ideas, and I would say, just preparing for this talk, I realized what an amazing 18 months it was between September '96 and FoSSaCS in March '98. And I'm very sad not to be at FoSSaCS and not to be at ETAPS today. I mean, Luca and I joined Microsoft Research. There was a ton happening in the UK that I just remember this period. Tony Blair became Prime Minister. There was the sadness of the death of Diana. But also, Luca and I were both really into computer games, and especially into Tomb Raider, which launched in 26 October '96. So when I think about the ambient calculus or the invention of it, I also think about Lara Croft. It was just an amazing period. So let me end there. Thank you ever so much for this opportunity to speak about ambience after all these years.
Thank you. Are there any questions for Andy? So it seems that after all these years, you were able to explain it in a very clear manner, so that nobody has any questions for you anymore about this. Well, one thing that I was wondering, so you said, okay, there was follow-up work, but the things you mentioned were all in early 2000s. Do you think there's still influence of what you've done these days? Do you still see that?
That's an interesting question. It's been a long time. I think, I mean, yeah, I think in biology, I mean, I would never go active in the applications in biology, but I think it led on to like a theory of something called brain calculi and other such formalisms. So I think there is still a lot of interest within biology to have formalisms for thinking at a sort of higher level abstraction than, say, DNA, but being able to think about what happens like on the surface of cells. And I think what we did had an influence there, for example, and I mean an ongoing influence.
Okay. Interesting. So then I would say let's thank you again. Let's thank Andy, congratulate him, and I hope that you might remember it was my first conference, ETAPS '98. I think we had a beer together while Bart was explaining the, what was it, Gala connections. So I hope we can have a beer together at some point in the future very soon. So thanks for being with us this afternoon.
That'd be great, Marika.
Yes.
Thank you so much.